In the first part of this lesson, we're going to talk about a way to define lines in R3. R3 is three-dimensional space, and I've used the word here straight. I used the word straight because in three-dimensional space, a line can refer to any curve. It doesn't necessarily be straight. So let's narrow that down and say we're talking about straight lines. I'm going to go ahead and label this line L. Now, to give this some perspective to see where this line falls, it's going to label a point there. And that point, if I drop down to the Cartesian plane, is here. And you see that that has a y-coordinate and an x-coordinate. And then that line is sort of going off into an angle. Now, keep in mind the method that I'm showing you here, there's no exact science to this. I mean, at one point, mathematicians decided how they wanted to define this line. I mean, you could have the same exercise and decide a way that you wanted to define the line. But here's what they came up with. A line, if you think of a line as a sum of vectors. So let's label this first point here, x naught, y naught, z naught. That's that point right here. And then correspondingly, we have a vector, and the vector is r naught. So that goes like this, r naught. So here, r naught, vector r naught. I'll put a vector sign on it. If I could bold it, it would be better, so I don't have to write this arrow, but I can't necessarily bold it with ease. So r naught is the vector x naught, y naught, z naught. Now, we don't just want this terminal point here, we want all the points along this line. So if you take that vector r naught and you add to it a whole bunch of other vectors, so let's say we have a vector here, and then the tip of it defines that point, and then another vector, and the tip of that vector defines that point, and perhaps you have one going down here this way, and a whole bunch this way. So if I take all those points that sum r naught plus some vector, those points will make up the line L. So using some function language here, essentially what I want to do is have some domain that's an element of R1. So that means I have one variable, and I'm going to map that one variable to R3. Said simply, I input one variable and I output a three-dimensional variable. That three-dimensional variable would be x, y, z. That would give us the line. So we desire a vector function, so I want r of, and I'll use the parameter t for my input variable. And what I want to do is I want to take this vector r naught, and then I want to add to that vector t, a scalar multiple, times some vector, and we're going to use pink here to be consistent, some vector v. Now, vector v is this vector here. And you will notice that this vector here, let's just, for simplicity's sake, say that vector v here is the vector a, b, c. And so all the pink vectors that I've drawn above here are all parallel to that vector. So this vector v gives us a direction. You can think of it as like the x slope, the y slope, and the z slope. And I feel like I want to show this again one more time just so it's crystal clear. If I take vector r naught, that brings me out to here, and then I add to it vector v times some scalar, that gives me that point. The reason it gives me that point is because when I add the two vectors, tip to tail, it points to that, and so that vector points to this ordered pair, whatever this ordered pair is. And then another tip to tail vector comes out to here, giving me this point. Some with a negative t would give me these points, so on and so forth, to construct the line. So I'm just going to continue down here and say that r of t, the vector that defines the line, is equal to, now vector r, I'm going to write it with its components, x naught, y naught, z naught, so I have a point on the line, plus our parameter t, our scalar multiple of vector v, and I called vector v a, b, and c for simplicity's sake. And that gives me a vector equation of the line. See, I input t, and the output is x, y, and z vector. Okay, and another alternative way to write this is you can say that the x component is going to be x naught plus a times t, comma, y naught plus b times t, and z naught plus c times t. And to ensure that this line goes on forever, we would have the domain t is an element of the reals. I'm going to write this one last time in the fancy function notation. So f is a function that maps t to the vector x naught plus at, comma, y naught plus bt, comma, z naught plus ct. So that was the vector equation of a line. Now the parametric equation of a line is simply to say that x is equal to x naught plus a times parameter t, y is equal to y naught plus bt, and lastly z, or z of t, is equal to z naught plus ct, where the line is parallel to the vector a, b, c. T is an element of the reals. Now this simple example will illustrate that the only thing you need for this equation of a line is you'll need a point on the line and you'll need the parallel vector, and then this is real straightforward. The vector equation of this line, r of t, is equal to -2, 1, 6 plus t times 7, 8, 9. That's the vector equation of the line. We want to make sure that we say t is an element of the reals. And then here we have the parametric equation for the line. Now your author also talks about something called a symmetric equation. Essentially what you're doing here is you're solving for t, and I have to be honest, I'm not 100% sure of the utility of this, but if you solve each one of these for t and then set them all equal to each other, let's see, we would have x plus 2 over 7, and that would equal y minus 1 over 8, and that would equal z minus 6 over 9, and we call that the symmetric equation. I may ask for that, the homework may ask for that. Again, I'm sorry to say I don't know exactly what benefit that provides for us. And this lesson on lines is very, very, very simple, but you really do have to understand the theory behind parallel and all that. So understanding the construction of the line as the sum of two vectors is very important, and this idea of parallel. So don't take it for granted, and the homework questions are way harder than the example here, so it's important that you practice all of them. You'll see it's pretty challenging at times. Next, we've got to figure out a way to define a plane in R3. As a hint, we're going to use vectors. Now you'll probably just watch this video and accept what I'm saying, but you might want to press pause and think about it for a moment. How the heck are we going to define a plane using vectors? One of the hints that I'll give you is that we know a point on the plane. So this point here is on the plane. Let's label that x naught, y naught, z naught, an ordered pair on the plane. And like before, we are also going to associate that point with the vector r naught, which points from the origin out to the point, and we're going to call that r vector naught. And somehow we have to get all the points on that plane. I'm kind of going slow on purpose and trying to give you some hints along the way. Now, another hint I'm going to give you, this is a pretty big hint, is I want all these vectors, the terminal point, of course, of all these vectors. They're going to have different lengths, but all of these vectors, suppose that all of these vectors are on the plane, and I add up all the terminal points of all these vectors on the plane emanating from the r naught point, then I will have my plane. But what do all of these vectors have in common? Every single vector on the plane has something in common besides that it starts at the point x naught, y naught, z naught. And here's the giveaway now. All of those vectors have in common a normal vector, or a vector that they are orthogonal to. See, this green vector here, which I will label n vector, will meet each of these pink or purple vectors at a 90-degree angle. So every single one of these vectors are orthogonal to the normal vector. And so the plane that we want is going to be obtained by considering all vectors v such that, again, they are orthogonal to n. Now, how do I mathematically describe that? So I'll say such that, and they will be orthogonal if v dot n is equal to 0. That is, such that the vector, now I got to back up here for a second. So how do I define each of these vectors v? So let's come back to our diagram. Here's where all the vectors begin, and they all end somewhere out here, another point on the plane. Come down here to kind of clean things up a bit. So again, we have a point on the plane that we'll know, and that's x0, y0, z0, and then we have our vector r0 that goes out to that, and we've got that established. Now, a whole bunch of, or all of the other points actually, will come as terminal points to vectors, and that vector can be anyway. So generically, I'm going to just call that vector r, which is then going to be the point x, y, z, opposed to this initial point x0, y0, z0. Let's just come over here for a second. So r naught is the vector x0, y0, z0. The vector r is the vector x, y, z, representing all the points on the plane. And then our vector n, let's just say our vector n, for generic sake, is the vector a, b, c. Remember, this is the normal vector. Okay, so vector v then, how do I determine what vector v is? Well, I hope that you see the vector v is simply vector r minus vector r naught. Whew, deep breath. So let's come back. We want to consider the plane is obtained by considering all vectors v such that v dot n equals 0. In other words, r minus r naught dot n equals 0. So let's come down and do that. So r minus r naught dot n is equal to, well, that's going to be x minus x naught, y minus y naught, and z minus z naught dot vector n, which we said generically we'll just label as a, b, c, and that has to equal 0. Okay, so if I do my dot product, then I get a times the quantity x minus x naught plus b times the quantity y minus y naught, and this should start looking familiar to you, c times z minus z naught, very important, equals 0. And so an equation of this form will tell us we have a plane, but it also tells us that the coefficients a, b, and c are the components to the normal vector. And from last year, post AP, we talked about how to get a normal vector, and of course that is the cross product of any two vectors in the plane. If I just come down here now and simplify this, we could say ax plus by plus cz, and that's going to equal a times x naught, that's a constant, plus b times y naught plus c times z naught. All of these together should be some constant. ax plus by plus cz equals some constant k. Let's take a look at this first real simple example. So write a vector that is normal to the plane, and then they give you a plane here. Now, this is so simple because we just talked about that the coefficients to x, y, and z are all going to make up, there's a 1 here, they're all going to make up the normal vector. So the solution is that the normal vector has the components 2, -3, 1. Now keep in mind there are an infinite many of normal vectors. Any scalar multiple of that vector would be a solution to this, but all they simply wanted was a normal vector. Now the next example is a little bit more time consuming. We're going to write the equation of a plane that passes through, and they give us 3 points here, P, Q, and R. Now we need two things. We're going to need a normal to this plane, and to find the normal to the plane, we're going to need two vectors in or on the plane. So let's determine two vectors on that plane. I'm going to pick two vectors on this plane. Vector 1 I'm going to pick is going to be PQ. To find vector PQ, it's simply the difference of the corresponding components. So that's going to be the vector -3, -1, -3. It doesn't matter which 2 points you pick as long as you pick 2 points. And the other vector that I'm going to choose to pick is vector PR. Again, the difference of the corresponding components is going to give me 4, -1, -1. And so now to find the normal to the plane, I'm simply going to take the cross product of PQ and PR. And I'll just, to be thorough, I'm going to write out each of these. So that's PQ cross PR. Okay, and we set up this little diagram. We did this last year at the end of AP. If you don't know how to do a cross product, you definitely got to go back and review this, because this is assumed that you know it. So we take the cross product, and that's going to give us the vector -2, -15, 7. And we explained that in order to come up with an equation of the plane, we needed a point and that normal vector. And so we can pick any one of these points. I'm going to go ahead and pick the first one just because it's the first one. And so we have -2, that comes from here, times x minus x naught, and because I'm using this point, x naught is equal to 1. Then I have -15 times y minus 2 plus 7 times z minus 3, and I have to remember that this equals 0. So there is the equation of the plane. Now if I put this into some kind of standard form, which means we have ax plus by plus cz equals a constant, and the leading coefficient is positive, then I have 2x plus 15y minus 7z equals 11. And there we have the standard form equation of the plane that passed through those 3 points. Again, now this example, although you may need to review a cross product, this example is considered very straightforward. You have to really focus in on normal, what is a normal vector and how does it relate to the geometry of space when it comes to planes and also with lines. So this is really an important chapter to do all the practice problems. In fact, the exam will come primarily from this lesson.